and the last day of ATAL FDP online program. So, the yesterday speaker, Dr. Roman Babu from IIT Tirupati. I welcome you, sir, on behalf of Department of Civil Engineering, University Institute of Technology, RGPV Bhopal. And today's expert talk of sir is evaluation of performance-based seismic design. I welcome you, sir. Uh, Sir, over to you.
Okay. Thank you, ma'am. Welcome to all the audience for this last day of the uh, training session. And today is my second lecture. Okay. So, yesterday I talked about uh, kind of the energy dissipation and that retrofitting, what we need that we talk. But today is a kind of the performance-based design, and extensively I will talk about all the design related, how the evolution of the design has come up, and and yesterday topic also I'll try to fit in this today lecture, and that you will get better idea. And in today's talk, like yesterday, I'll cover many others portion also. And some of the thing I try to correlate. Sometimes when we talk about the performance-based design, only we are thinking about the structural performance. But how to achieve that structural performance, still people did not much look towards that side. So I'll focus on one of the very key area, how to achieve that performance-based. And anyway, before coming to that, let's talk about that overall design steps, what we follow up in the since after independence. Okay, so whatever the design method we use, and the first design code we have, actually it's not a design code, it's a design guide, it's IS 456. So IS 1893 and 13920, it comes in the later stage. So we heard that even in the reinforced concrete design, and we heard that working step method. Simply theoretically we learned it, but we never nowadays, except in the water tanky reservoir or something. That area is still we are doing the working step, but everyone is not doing that type of the design. So means more or less people not much aware about the working step method. That's our first, we can say, step of the design what we learn. Then in that working step method is revised in the 1957. Second revise happened in the 1964. Then in 1978, third revise, and here the some limit state concept was introduced. Okay, so in the 2000, the IS code 2000, IS 456 2000, this is currently people use. This is the limit state method. Okay, before that, that's the working state one, and but in 1978 version, some limit state criteria has introduced. Okay, now when we talk about this performance-based design, the performance-based design also come up in the 2000. Okay, then what is our next goal? The next goal is the next generation of the performance-based design. Currently, what we are doing for both performance-based design as well as a next generation performance-based design. So for time being, better not to look towards the next generation. First of all, let's try to understand what is a performance-based design. Okay, so before moving to that performance-based design, let's try to understand some basic concept of the that design. What is recommended by IS 456, and IS 456 is a recommended document only for the plain concrete and the reinforced concrete. And over so as I mentioned in that timeline chart, it was published in the 1953, and at that time the name of the code is called Code of Practice for Plain and Reinforced Concrete for General Building Construction. And after revised in 1957 and 1964, the name of the code has changed to Code of Practice for Plain and reinforced concrete, enlarging the scope of use this towards the other general building construction. Okay, in the 1953 it focused only in the general building, and after 1957 and 64 it expand to the other construction as well, and it was restricted only for building, but after that it expand for other components, other buildings, other structures also. In the third revision, the walking state method, this was fully mm, involved, as well as some limit state was introduced. And in the fourth revision, 2000, the plain reinforced concrete, or maybe the code of practice, so included a limit state approach. Okay, include the rapid development of the field of the concrete technology, that also is involved. So means each and every revision, the new terminologies is come up. And at the end of the today talk, I'll cover what is the upcoming IS 456. Currently we are using IS 456 2000, but this code will be will not be used anymore. After 1 year or 2 years, we are going to be use another new IS 456. Okay, aspects of the that 456 IS 456 I'll discuss in the upcoming slides, most possibly at the end. So now in this IS 456, the plain reinforced concrete code of practice, it is mainly focused on the limit state of the collapse, that is safety, and limit state of the serviceability and the durability. This three parameter is the one focus on that code in the current IS 456 2000. Okay, in 2000. I'm not talking about upcoming. The upcoming code is much more rigorous and is much more robust than the this current criteria. Please note down these three parameter. Then what is the scope and what is the deal with? And it deals with general structure used for plain and reinforced concrete, and the plain concrete structures, those where reinforcement, if provided, is ignored for the determination of the strength of the structure, and it is inapplicable. So IS 456 is not applicable in all structure. Some structures are inapplicable, and those are the chimney. When you go for the chimney design, means it's a kind of a slender, tall structure. So IS 456 is not applicable. And like cell structure, hydraulic structure, liquid retaining structure, arches, bridges, folded plates, the blast resistant structure, the earthquake resistant structures, IS 456 is not incorporated. It means it's not applicable. IS 456 2000. Okay, in upcoming things, some of the already things is incorporated. And whatever point, the first slide to the previous slide, it was a kind of this overall design concept what we use in the current day-to-day life. As a faculty, you have taught the reinforced concrete design, or maybe as a practice engineers, you did lots of consultancy projects, and you did the beam design, column design, and frame design. Everything you focus on that code. So IS 1893, that is the only code giving the seismic load, and after applying the seismic load, whatever the bending moment shear force come up, for that how you design based on the IS 456 criteria. Okay, so now after having that a short information or a short summary of this design history, let's look towards the history of the performance based design. So I will not go very fast. Let's spend a little bit more time on this. First of all, what is the performance based design? What is this? And the performance based design was no exist before 2000. Okay, before that there is no call a performance based design. And the main document, there's one document called SEOC Vision 2000. That was the kind of the main document just to develop the performance based design. And this SEOC document, which published in the 1996, it focused on it is a document which procedures that enable design and construction of the buildings that will be reliably be able to attain desired seismic performance. It means our required performance is kind of is highlighted in that document. And those three performance was kind of the potential life safety impact, potential loss of the occupancy, and the potential repair costs. Okay, these are the main topics which focus on that. That's the landmark report just to develop the performance based design what currently we're using. And so it is an approach to obtain a building that perform better than the typical code conforming buildings. And that's also the building don't meet the code but can perform as well as a code conforming building. What does mean that? So it means some of the that building perform means need to be attained, and that code, what is the building code? Okay, first of all let me put a one point. Up to last section I was talking about Indian context point of view, but currently this performance based design what I'm explaining, that is not in the Indian context, that is in the Western, that American code point of view I'm speaking. Okay, so sometimes some point might be deviated, and that please try to understand it. So later on I'll just compile everything and you'll get a better clarity. So they use the building code, and that building code might not be able to explain all kind of the this performance what we require. But how this performance based design come in the picture, and who is the responsible for that? Okay, how it come up? Is it come automatically, or simply we develop this code? Answer is exactly no. That I'll just give that explanation. So the decision maker stats desire that the building able to perform in a certain way. Okay, so means whenever you design the structure, the buildings should be able to perform in such a way that it should be able to protect the life safety. That's the one of the most important parameter. But in the when you go for the this one limit state design, the safety factor is considered. The safety means what is mean that safety? The safety might be the collapse limit safety might be considered, the material safety factor, but life safety factor is not considered. So that's the one of the most important parameter involved in the performance based design. And try to understand the what called safety. Even in the limit state also safety term is there, but in a performance based design also the safety term is there. But what are the safety we are considered? In the limit state design we got material safety factor for the 1.15 1.5 for the concrete, 1.15 for the steel. So what type of the safety it considered? Is it safety for the structure or safety for the life? That's the questionable. But in the performance based design it clearly mentioned that that's the safety for life. And meanwhile it has to consider the minimal potential repair cost. So means of course we know that during the disaster time might be earthquake or might be tsunami or wind, a tornado, during that structure will be damaged. Of course the damage, all the damaged structure will not be demolished. That's how the retrofitting come in the picture. So means the repair and retrofitting, that minimum cost has to be, because of course we say the performance based design structure should not be collapsed. I agree the point that after the disaster structure was not collapsed but it was tilted in the 20 degree. But just to bring back to structure in the normal position and again repairing cost, it might be so huge. Sometime better to be construct a new house. Then what is the point of your performance based design? It means performance based design means structure should not be collapsed, but meanwhile it should, the deformation should be in the minimum level. It means your repair cost also will not be high. That's the second point. And minimum disruption of use. Minimum disruption use means what? Especially for residential building, somewhat you can manage it, but like a city center, or like some kind of a business hub area, or maybe some kind of the data center area. So means once if it is damaged, it might not be able to function immediately. So means if your banking system is not function for a week, what will happen to our society? And currently nowadays this one, lots of multimedias are there, and the internet service is, if the internet service is stopped for 1 month, so that type of the things also come in the picture. Okay, whenever you grow your lifestyle, our design also has to be updated. That's the performance based design. Okay, so means there should be a minimum disturbance. Okay, so within a short period of time, you can resume your duty on that building. So that's the another aspect of the performance-based design. And whatever point what I highlighted here, that is not considered in the our existing the performing the design codes like in the limit state and others. It is not incorporated. Now that's the wishes. Whatever the point I highlighted, that is our wishes. So building should have that level of the quality. But who will get this that service? Who will provide it? We are the engineers. We are the one developing these things. So we are the responsible just to give that level of the uh, expertise to the people, and we should give the solution to the people. That's how we should work it. Okay, so now here the capability of the engineers come in the picture. So in the football ground, who are playing? In soccer players are playing, and incapable players are not able to play properly. Similarly, in this type of the design, and when we go, only those people who are very strong in a design, or they can give this service, but many engineers are there who are incapability of doing such level of the work. So they should be improved. Okay, just for the society. Okay, as a responsible engineers, we should able to give this level of solution to the people. That's the thing we have to look at. Now let's talk about this performance based design code. And so now if you look, that's American standard, that is known as a IBC, International Building Code. But in terms of the Indian point of view, IS 1993. So 2016 version is there. So earlier it was 2002 version. So now it's 2006 version currently we are using. So this is our, you can say, our earthquake design code, and it considers the performance based design criteria. But one thing design approach. Okay, but contradictory thing is we design the structure based on the force, but we check the performance of the structure on the displacement base. Okay, it did not mean that we design the structure in the displacement and we cross check in the displacement. It's not like that. Whatever our design we did based on the force only. But the cross verification and the performance objective, everything is defined in the displacement. Please make clarity about this the criteria also. So if you open any of this design code, you can find out the yield force and the base shear force, everything in terms of the Newton, kilonewton, kips, you'll get it. But when it talk about the performance point, it will express in terms of the drift, 2%, 1% drift, and 1.5% drift. That level only people will talk it. Same thing happened to your limit state design. Even for IS 456, when you go, how you designed it, you designed the shear force, you designed the moment. But how did you check the serviceability? The serviceability, you check the deflection criteria. Okay, L by 20, L by 25 for simply supported condition. For the continuous support condition, you are checking the deflection criteria, right? So it means whatever our design, so limit state, the performance based design also is updated version of your limit state. So don't think performance based design is a totally different design of the existing. Your concept is wrong. Performance based design, if you look in details, is very simple. It is a just updated version of your limit state design method by introducing some other uh, factors, extra factors are introducing. That's it. So in this code, it provides minimum acceptable lateral strain and stiffness and the minimum acceptable detailing practice. Okay, the required attachment strength displacement capacity of non-structural component also. It is required. It need to improve. That's how this third point we'll talk about the next generation performance-based design that I'll cover after some few slides. And here the word called minimum is used. Why? The minimum means okay, the performance-based design in some other way we can say it is the earthquake resistance design philosophy. That also you can say. But why we term use called minimum? Because if you use a maximum value, of course your structure will be very safe and sound. But will you able to bear the cost of that construction? So that's why I use the word called minimum just to have, just to resist that level of the force, and your structure will be safe. That's the philosophy currently we are focusing. Now, the presumed to be provide acceptable performance, actual performance capability never actually evaluated. Okay, that's the point we have to be remember. Now, let's talk about this the history of this list of the earthquake. As I mentioned, the performance-based design was developed from that Western country. You see the US is the one of the country who took the main lead work and developed these things. Of course, that's Japan also in but the major work happened in the US. Okay, so this 1971 to 1994, this is the period people working in depth just to develop your performance based design. And in this period, a series of the drastic level earthquake happened. That too all are above 5.5 magnitude. 1979, Imperant Valley, some of our faculty colleagues and research scholar or maybe the MTech students, see in your dynamic course or maybe in the earthquake courses, you might heard this name of earthquake frequently. And now you can correlate why we frequently correlate those earthquake name in that course. So because if you look 1979 Imperial Valley earthquake, 1983 Kolinga, 1984 Morgan Hills, 86 North Palm Spring, 1987 Superstition Hills, 89 Loma Prieta, 92 Big Bear, 1992 Layers, 1992 again Cape Mandino, 1994 Norris, 1995 Kobe. These are the famous earthquake. And these earthquake names are commonly used currently in your dynamic course or maybe in the earthquake engineering course. The reason is the performance-based design was developed based on this list of the earthquake information. So means during this earthquake, the building has performed in an unacceptable level. People are very upset. Okay, they thought that their building is safe. That their building is designed based on the IBC
ये बस ऑफ होने वाला
कुछ हेडफोन थे वो पिन वाला जल्दी से या हमारे बैग से दो बैग को दे हमारा बैग से दिखा व्हाइट कलर का चार्जिंग है व्हाइट ये चार्जिंग किसका है चार्ज नहीं है
है। ये जाने वाला
उसको बोल दे रहे चार्ज
है। ये वापस से ओपन हो जाता है। चालू हो जाता है इसमें। ये डिस्कनेक्ट होता तो यहाँ से चालू हो जाता ना।
ठीक है ये चार्जिंग को लगना है ना
हाँ
फ्यूल बेटा देखो चार्ज वापस नहीं
सर डिस्कनेक्ट हो गया। नेटवर्क इशू आ गया क्या? काम तो नहीं आ रही है।
Uh, am I audible? Dear participants, please wait. I think so. There is some network issue with the expert. Please wait for his session.
Yes, ma'am.
I'm calling him, but I think so. He might be busy. Please wait.
Yes, ma'am. Yes, ma'am.
Thank you.
कुछ नहीं वो अपने यहाँ बात चली थी उनका क्या हुआ क्या बोलूं फिर उनको? हाँ, आपका कनेक्शन नहीं हुआ है, आप लेफ्ट हो गए हो मीटिंग, सब लोग आपको वेट कर रहे हैं। हाँ, हम देख ले रहे रिकॉर्डिंग में से किस
Yes, sir. Yes, sir. Now,
Yeah, actually, there is some kind of the interruption in the connection. So I think it automatically left out. So may I know up to what slide did you observe?
yes, sir. Please share your screen. Dear
Yeah.
participants, please check at which slide it was stopped.
Is it this slide? Life safety here?
Yes, sir.
Okay.
Yes, sir.
This one has cover or not? Actually, I was talking about the 0.7 and 1.5.
Sir, you can continue with this slide.
Okay, fine. Thank you. Okay, so I don't know at what point it was exit. I'll repeat the life safety. For the life safety, so the first demand is the life safety. For that, we increase 75% from the existing lot. Existing lot means the normal design lot. That immediate occupancy means what I mentioned, the important structure like hospital, station, police station, or central facilities. For such type of the service station or by some building, it should be able to occupy it just after your disaster events. Okay, so now that's how we should uh, apply more load, because this is more important. So it will be the another 75% has applied it. It means altogether 150% is one extra 150% has applied for the immediate occupancy type building. So this is not the permanent resident. This is the one we don't have any choice. There was no any document. That's why from the existing building code, this is uniform building code. Okay, in this code itself, we apply extra forces. This is the first step of your performance-based design before existing any code. This was in the 1990, you can say 1990s. Now, the probable maximum loss, or the PML phenomena. What is that? Probable maximum loss. So currently, insurance company, the insurance company, we have life insurance, we have your vehicle insurance, you have the insurance for different of your gadgets. But the building insurance, is there any building insurance in India? But I'm not sure. Some area it might be initiated. So I don't have any kind of the confirmed data on this. But in other country, there is a building insurance also is there. And just to enroll that building insurance, the company, they are calculating the probable maximum loss. Okay, PML. So if the repair cost is more than 20% of the replacement value, then the guy can't get the no insurance company. Okay, none of the company will give insurance on that building. So another factor that's also considered. So minimum damage has to be there during the earthquake. Then only you can claim you can get the enrollment of your insurance. That's also another factor. It become in the late 1980 series. Before in the early 1980 series, we talk about the life safety, we talk about the immediate occupancy, and see, day by day the demand from the people is keep increasing. Today I say, tomorrow I'll say the immediate occupancy. Next day I am just telling, no, actually, apart from life safety and this immediate occupancy, I need another parameter. My building should be damaged as much as minimum, because I need the certificate. I need a certificate of minimum damage will occur during the disaster. That's another condition. Otherwise, that guy will not get any benefit from the insurance. So just to certify to structure, you have to improve the building performance, and that damage has to be within the 20% of your repairable cost. That's how they got that insurance, and that's also another game changer for the performance based design. So owners started asking to upgrade their building to have at least minimum 20% of PML. And it was really challenge for engineers. So we don't know when that structure was constructed. It might be 10 years old, it might be 50 years old. But anyway, the damage should be within the 20%. How to improve? Because whatever the discussion happened here, all are related to the existing building. Am I right? All are existing building, not for a new construction. So for a new construction, it's very easy, very simple. You have the freedom to change. You can increase the load, you can increase the dimension, you'll get your required performance. But whatever I took, life safety, immediate occupancy, PML less than 20%, these are owner of the structures, and all the structures already existed, and it become the different years. Some are 10 years, some are 20 years. Okay, now then how to minimize the repair costs, the PML value? We really don't know. What percentage should we put on the code? What we put in the code previously for the life safety, we use 75%. For the immediate occupancy, what we applied? We applied another 150%, another 75%. Means 75, 2 times become 150. That means now the minimum repair cost, how much load should I increase? This is a Y factor. Y should be 200, should be 300, 500. No clue, no solution. Because linearly we applied some kind of the assumed value for those structures. Okay, that's how now that was up to the late 1980 series. And considering all this issue, in the early 1990s, FEMA funded ATC. That's how your right now those people who are working in the performance-based design or others, you know that FEMA documents, ATC document, and ASE documents we're using. But how those documents are come up, this is the explanation. This is the real history of those documents. Okay, to develop a landmark project, Once ATC 33 project was funded, and which is ended eventually publication of the FEMA 273 and the FEMA 274. So ATC 33, that project was deployed, and at the end, as output of that project, FEMA 273 and FEMA 274 has come off. This is the guideline for the seismic rehabilitation of the building. Okay, this is seismic rehabilitation of the building. The other was ATC 40 documents. Okay, that's the seismic evaluation and the retrofitting of the building. Two documents. One is 273, 274 FEMA, that was dedicated for the rehabilitation, and the ATC 40, currently you also might be used that is the seismic evaluation and the retrofit of the concrete buildings. That to concrete, not for the steel structure, that for the concrete. So the rehabilitation term and the retrofitting term, they use in a different. That's what yesterday I told. The retrofitting term is a different, it's a science. We need to use this terminology very precisely. Until and unless if you don't have any kind of the proof, document, or scientific support, you are not supposed to be used the term called retrofit. That comment I put yesterday. So after publishing this document, the same team, and with few new members, develop a similar document from the different funding. Of course, the funding agencies are different, and they develop the document called ASE 41. Currently, what you are using. So FEMA 273, ATC 40, ASE 41. See, they are from the different funding. And ASE 41 is a seismic rehabilitation of the existing building, and currently this document has updated to the seismic evaluation and the retrofit of the existing building. ASE 41. It is changed the name. So now I can say the ATC 40 was the first document which is developed for the performance-based design. That too in the 1996. Okay, and the FEMA 273 was published in the 1997, and the ASE 41 was published in the 2006. Because ASE 41 come much later, the team of this ATC 40 and the FEMA 273, they jointly work together and come up with the ASE 41. So this is how the performance-based design has born and has grown up. And currently, we implement in the different country codes. And one thing, please keep in your mind, this is the first true performance-based design standard document. And one thing, keep in your mind, the performance-based design was developed for the existing building, not for the new building construction, not for the new building design. Original performance-based design for retrofitting and the rehabilitation. So currently, the performance-based design has extended for new building as well. So don't confuse, the evolution of performance-based designs come from existing building. Now, the short steps how to proceed for the performance-based design. First of all, select the objective, performance objective. Okay, mine is a residential building, and in the 50 years, I have some kind of the moderate level earthquake might come in this area. So my structure should not be collapsed that point. Like that, you have to define your objective. Accordingly, you do perform the preliminary designs. For the Indian, use IS 1993. For the American, use the building code. For the Australian code of practice, you can use it. New Zealand code and the Japanese code. Different country has a different code, and they have the different design criteria are there. Logics are same, but the values are different. Don't think the American code and European code and our codes are same. Concept is okay, concept is fine, but value will be different. So assess the performance capacity by analysis and check the acceptability. Okay, as per your analysis, is it acceptable or not? If it is no, then you revise it. This is the kind of a very simplified form of the your performance based design process. But actually, if you do the performance, it's lots of many steps are there. It will take time. Assess the performance capability. This is one dialog box only I put here. But how to assess it? You have to do the pushover analysis, and you have to find out immediate occupancy collapse level and the hinge property assign. So it's a lengthy process. Okay, it's a lengthy process, but you need to learn all those things. But whatever I presented here is a kind of a very short summarized steps for the performance based design. Okay, now how to define the performance objective. So you know that yesterday I talked about the tectonic movements. What are the active faults and others? Okay. For example, now you plan to construct your building in your city. Okay, your city might be in the seismic zone 2. Okay, in that seismic zone 2, in the 50 years of this span, what type of the earthquake might come, that you have to evaluate it. Okay, the same kind of the building, if you want to construct in Uttarakhand or might be some in the northeast region, then you'll have a different earthquake forces, because there belongs to the seismic zone 5 and your city is in the seismic zone 2. So you find out what is the expected ground motion 50 years, because the 50 years we consider as a lifespan of the building. Okay, so now design the hazard course. So means, okay, we have to define in the minor shaking, this same slide, same photographs I have shown in the yesterday also. In the minor shaking, there can be some kind of the micro cracks on the wall. Okay, in the moderate level of the shaking, of course, major cracks on the wall as well as a minor yielding on the beam. Okay, in the major earthquake, the strong earthquake, the wall will be extensive damage and the ultimate level will be reaching in the beam and the yielding on the ground column. That is your performance objective, what we usually decide. Okay. Now, as per the ATC 33 and ATC 40 project, what I mentioned, this is how we define the performance objective. Frequently, in 43 years, frequent earthquake will come. That time your building should not be damaged. It should be in operation condition. An occasional level earthquake, okay. So your building should be operational, not fully. It should be operational, and the real level earthquake, it should be life safe. Okay, and with shear level earthquake, your building should not be collapsed. Okay. For anything else?
Yeah, sir, join me, sir.
Okay. Yeah.
Oh.
Okay. Thank you. 1 second. Thank you. So similarly, for some other structure, you have the different hazard performance for example, when you construct for some nuclear power plant, this objective will not be applicable. You have to define a different objective. So whatever defined here, this is for the normal residential building, and this upper portion is not at all acceptable condition. Okay, so same diagram if I explain in terms of the building performance. So This is called a pushover curve. The pushover curve we found from the pushover analysis. And the first thing, operation. The operation means your building will be within the elastic region. And immediate occupancy means structure will be yielded, but it will have some kind of the a mild deformation. So means the life safety means is more towards the uh, collapse area, exactly not resting. So finally, that is a collapse. This should be in a very sure condition. Okay, so this is our overall uh, design objective for the performance based design. But if I talk about the limit state and the working state means only it will focus in this region. This portion is not at all considered it. Okay, now let's talk about this performance could assess with the help of the nonlinear pushover analysis. And some of you might have used the SEP 2000. The SEP 2000 is a CSI based software, and along with this ATC team, the SEP 2000 was developed dedicated software towards this performance based design. So after SEP 2000, many software has developed like Perform 3D and like ETFs, and many other softwares also come up, and they also have the capability for doing the pushover. But the SEP 2000 software was the basic software which developed to evaluate the pushover analysis and the time history analysis. Okay, even in your design of earthquake code or earthquake courses or dynamic courses, you might learn that the response spectra method or maybe the time history analysis method. Okay, those are also part of your performance based design. Now, the structural performance, how to design it. So during that pushover analysis time, you have to assign the non-linearity on the structural components, especially on the beam. You have to assign a kind of the uh, M5 relationship. Okay, M5 hinge property has to be assigned, as well as you can assign a shear damage V versus delta. You can assign for the beam member, but for the column member, you can assign like PM3 as well as a shear B and D. This is a P versus M. So this shear hinges to be assigned. Okay, based on that, you can identify this immediate occupancy, LSCP. Those things already have a very well developed relationship was given in the ASE 41 or maybe the ATC 40 or maybe the HEMA 273. Whatever the document I mentioned, it explained very clearly. So after that, if you do the pushover analysis, you will get some capacity curve. This capacity curve is known as a pushover curve. Okay, so as a lecture, I'm just giving this pushover portion in a very short way. But actually, if you want to do the pushover analysis, you need to spend a little bit more time. Okay. So, but I can't cover those things in this short period of time. So, but during the even in my course, my MTech courses, I usually taught this pushover analysis, time history analysis extensively by taking another 5 or 6 classes with the demonstration hand-to-hand practice. But in this short period of time, I can teach to that level. Now, whatever we are talking, that is for your non-structural structural performance point of view. We discussed that the beam performance, column performance, we are talking. But did we ever talk about a non-structural performance like false ceilings, like electrical fitting, like water pipe connections? See, if you look to those non-component area, during the disaster time, the number of casualties come more from this damage, not from your
main structural component damage. So during the earthquake shaking time, some of your fan might be fall down, some almirah might be fall down, some water connection might be broke, electric shock might be happen, number of casualty, people will die. So here number one, account for more than 70% of the earthquake economic losses. Okay, not really covered by the present procedure. It means in the current design procedures, any kind of design procedure, we are not at all consider this kind of the non-structural component. Shall we ignore in the next level also? Because the major losses is come from this side only. The non-structural components are very expensive, and it is really creating your life in the miserable condition also. So that's how the next generation performance-based design has come up. As I mentioned earlier, the performance-based design, the next level will be the next level performance, next generation performance-based design. So in the next generation performance-based design, all these non-structural component performance also will be included. Currently that research is going on, the documents are in the developing condition, so you can have some kind of exposure after some few years, okay, regarding the next generation performance-based design. Here, this is the pushover curve, as I mentioned. Anyway, for the non-structural component also we need to carry it out, but only factor of safety will be changed. So this is the again how to evaluate the non-structural performance or structural performance component for the pushover using the pushover curve. This is explained here. First of all, you should design the structure considering the design spectra. From that you calculate the base shear, and the base shear has to be distributed, and you consider load combination. You have to carry out elastic analysis, find out the bending moment shear force, then you apply the nonlinear pushover analysis. The design is the elastic base, analysis is the nonlinear pushover. Then this same spectra here you overlap with your pushover curve. Okay, after overlapping there will be some kind of the cross section point, you will find out it. That is known as your performance point, the real performance point of your structure. Okay, so this is how we should go for the design of performance-based design. So I just here I show the different building category. One is a bear frame, one is a shear wall, one is your steel frame along with the BRV. Now, inelastic seismic response of the structure. This portion, the one which I bracket, this portion, just to carry out a pushover analysis, you need to understand the inelastic seismic response of the structure. So, under the lateral load, or might be under the earthquake, the deformation takes place in the structure. So, the earthquake load you can say is a kind of the cyclic load. It's a kind of the push and the pull. It did not always push. Okay, the pushover means pushover curve. That's the only monotonically you are pushing the structure and till collapse. That's your concept of the pushover. But in case of the time history or maybe the earthquake, it will be vibrate. Structure will be go positive side, negative side. So now in that cyclic type, based on your material behavior, structure will behave kind of different response, and push and a pull. This is known as your hysteretic, and your hysteretic material might be elastic plastic, bilinear, or general strength hardening. So means what does mean that? This is the kind of the graph you have response. So for the mathematical modeling, we can idealize such type of the model as a kind of the elastic and a fully plastic. And in some other condition, we can more simplify as a elastic along with the strength hardening. So now if you look here, this is a highly non-linear curve, is a parabolic curve type. But if you look here, it's a kind of the combination of the two elastic equation. Here will be one stiffness and here stiffness is 0. But in this condition, another stiffness and another two different stiffness you will have it. So this is easy for our mathematical modeling purpose. So that we have to understand it. Now this is the hysteresis behavior of the robust system. Like usually it don't have any kind of the pinching. But in case of the concrete, you will have the pinching. And now you can, pinching means it is losses of energy. Okay. So usually steel structure has don't have much pinching behavior. Of course it has, but it don't have much like concrete. But usually concrete structure has high pinching behavior. And this is the hysteresis behavior with pinch effect. And especially for the brittle material like glass or maybe the brick, it don't have usually the hysteresis. Whenever it increase once after yielding point, it break it. Okay, so within the elastic region, it might have some kind of the response like this, but it don't have the extensive non-linear hysteresis response. So this is the area under the hysteresis. So this area is known as a energy dissipated or maybe the dissipated energy. So whenever we talk about this earthquake resistance structure or any kind of the non-linearity, we talk about the dissipated energy. The dissipated energy means it's nothing, it is the area under the hysteresis. So we try to have as much as a high energy dissipation just to have the better performance. And yesterday I was talking about the energy dissipation device because we try to contribute more hysteresis area in the structure just to improve this dissipated energy area. So that's how you can correlate yesterday topic and today topic. So for that inelastic behavior of structure, see now if you take the structure, okay, if you take the structure, finally your pushover come in such a way that, but is it coming straightforward like this? No. That's first of all, this whatever you plot the pushover curve, that's the overall response of this structure, your structure. But this overall response comes from different sources. First of all, it depends on the material and depend on your cross section, depend on your critical region, and finally the structural level. So this is the hierarchy you have to be followed for the nonlinear analysis of the structure. So material level nonlinearity, cross-sectional level nonlinearity, and critical region, the plastic hinge formation, and the structural level collapse, that has to be understood just to get the pushover curve. So whatever topic I'm discussing, that is only the in that flow chart I bracketed one region, nonlinear analysis. Only for that section only I'm explaining. So means one section itself is a huge region. So to complete a pushover analysis, you need to understand and very hardcore structural concept you need to have. Okay, now from the material point of view. From the material point of view, we need to do the material testing. So in case of the metal base, we are doing the coupon test or maybe the dog bone specimen. From that, you will get the strain. Okay, that is known as your strain ductility. But this is the again bar tensile test. Whatever the previous one, that's the coupon test. This is a bar tensile test. And even in the bar, you have a different bar, the mild steel and the high YSD 415, FE500. From that, you'll get a very clear idea how the strain hardening is happen and what is the level of ductility. Okay, this is the again if you do the cyclic testing in the material level, before yielding, you will have such type of a very uniform elastic response, and after yielding, it will have some kind of the hardening, and you have a very wide range of the hysteresis also you get it. So here I'm going a little bit fast because such type of diagram is, you already know it. Okay, I'm not spending much time. So since the time is limited, I'll try to cover some other portion also as well. Now coming to the section analysis. The section analysis, this is the I section. In the elastic level, this is your strain distribution, okay, and this is a stress distribution, and your moment will be taken by this top flange. This is how we understand in the elastic analysis. And some of you might learn the plastic analysis. In the plastic analysis, still your strain, the strain distribution is elastic only, but your curvature value is more. So whatever here, the curvature is a yield curvature, but in this condition, you have to take the ultimate curvature. But your stress distribution will not be a elastic distribution. It will have a combination of the elastic as well as a non-elastic region. Like here, up to this portion is elastic region. Beyond this point, whatever hatching area, this is your plastic region. Same concept if you look towards the stress strain distribution. See, this, instead of hardening, if I modify it in such a way that, can you imagine in such a level? If you directly turn up this drawing, exactly it is same as this one. This is the stress versus strain. So since you move to the plastic level, the bending capacity on the structure, it is increased, and the wave portion also taking a mild contribution of the bending. This is an inelastic response, and this response we use for the pushover analysis as a hinge property, the section property. Okay, for the section we define, this is a kind of the moment curvature relationship, as I mentioned in the few slides back. For the beam, we define the moment curvature. So this ductility is known as a curvature ductility. Okay, curvature ductility. And in case of your material level, the ductility what we have, that's called the strain ductility. Don't confuse what is the strain ductility, what is the curvature ductility. The curvature ductility come in the structural the section level. The strain ductility come in the material level. So this is for the critical region, the plastic hinge. Okay, now when you go for the fixed in the structural analysis class, if you remember, if you analyze this fixed end condition, if you apply a constant moment, you'll have a rotation. If you apply it at the both end, you'll have such kind of the moment. And the corresponding curvature diagram also will be like this. That's it is in the elastic level. Now, if you apply it, your curvature a little bit more. If it is reaching the ultimate, your moment will be again distributed in such a way that, and your curvature start becoming the non-linearity, because the joint region, the curvature is more. Okay, this is the moment curvature thing what we are assigned in that pushover analysis. So this one, moment curvature, this is idealized form. So here it is represented by only one plot, but actual the distribution from it is shown here. From here you can learn a lot how the moment curvature is distributed, and in the elastic as well as the inelastic. So for pushover analysis, we interested in the inelastic region. Elastic is very simple, that you already learned in the analysis of the structural analysis in your BTech course. So this inelastic portion is very important. You should know what is the nonlinearity behavior of the material level as well as a section level. So if you look here, this is a column performance, how it got damaged during the earthquake. The shear diagonal cracks are here, and this is a kind of the typical response of that reinforced concrete column member. And high pinching, here is a pinching, lots of energy losses are there. So since there is a loss of energy losses, it can't resist much higher strength, higher forces. Okay, so that's also one reason. So we need, when you model this type of the column in the pushover analysis, you have to assign this value PM3 as well as your V versus delta shear. This hinges has to be assigned. So that is you can correlate to my previous slide. Then only you can carry out your pushover analysis. Now this is another critical reason for the steel section. And if you look to the reinforced concrete, the losses are here. But if you look here, the losses are minimum. But of course, the strength degradations are there. If you just draw that, it is a degradations are there. But energy losses, the pinching behavior is much lesser compared to your concrete sections. Okay, so this is a difference between your concrete structure behavior and your reinforced concrete structural behavior. So in the structural level, this is a kind of the repeated information. After completion of the section portion, now we should look to the structural level. In the structural level, under the pushover, all the beam has to be form yielded, and the ground column can be also yielded. Not the entire column, only in the ground column. This is the basic concept of your plastic analysis. So from that, you are getting a capacity curve. This is called a force versus displacement. And whatever ductility you are getting here, this is your structural ductility, mu. Can you remember? Material ductility is known as a strain ductility, and the curvature ductility, and this is the displacement ductility. Okay, it might be in terms of the inches or a centimeter or a meter. And from here only we are going to be define the drift of the structure. Okay, people express, as I mentioned, the design is carried out based on the force approach, but analysis and your evaluation is carried out in terms of the ductility. So right now, the last almost 10 slides, I was kept talking about the ductility. It means ductility means nothing that is related to your displacement. So ductility and the energy dissipation capacity, the structure should be able to sustain several cycles of the inelastic deformation without significant loss of the strength, and some losses of the stiffness is inevitable, and the more energy dissipated per cycle without excessive deformation, it is better to behavior of the structure. Okay, it is required, and a good detailing is required just to have the good ductility and the energy dissipation capacity. And now the ductility, the system ductility, it is around 4 to 6 is required for acceptable seismic behavior, because 4% drift to 6%, and especially for the reinforced concrete it might be 2.5, but in case of the steel structure it is range from 4 to 6. So for the concentric brace frame it's around 4.5, and for the BRB it will be around 6%. Okay, the good hysteresis behavior is required for ductile behavior. However, the ductility itself is insufficient to provide acceptable seismic behavior. So this is one of the most important points, and that's what yesterday I mentioned, that the ductility is still questionable some people don't like ductility. They want strength and stiffness. Cyclic energy dissipation capacity is better indicator of the performance. So in terms of the hierarchy point of view, if you look what I discussed in the last 10 slides, we talk about strain ductility, curvature ductility, rotation ductility, and the displacement ductility. These are the range of the ductility limit for the different material level and your section level and your structural level. So this is the hierarchy. Usually we are accepted value for the design of the structure. Then after understanding all this thing, so how to deal with the huge earthquake forces? So here only it come the yesterday topic will be applicable. Okay, I'll just try to correlate. So improve the structural section and the material performance. Yes, we say that performance-based design. We need to improve the performance. Logically, we are correct, but actually, when you implement on the field, how to achieve all those things? How to achieve? Because we need to use a good quality material, right? Just now we talk about the material level and section level. That is just to achieve your performance goal. So here, once if you use heavy reinforcement, because just to improve your performance, we need to have some kind of ductile behavior, and we need to have some kind of the very high reinforced sections. So that time, how to achieve? This is the way we have to achieve the performance point. But meantime, is it the correct way? Simply providing the reinforcement, can I get all kind of the performance? Answer is still no. Of course, here question of construction challenges and sustainability. So whatever the topic I'm going to cover in this few slides, this is most of the people did not correlate to this topic to the performance based design. But today I'll try to correlate it. Okay, now you need to improve the performance, but meantime you have the very heavy reinforced sections just to reach that performance level. But the construction, especially here, this is focused on your concrete construction and the role of the admixtures. We thought that in the institute people are doing the material research, people are doing the structural research, and some people doing the material research, only mineral admixtures, chemical admixtures they're doing, and the structural people are not at all bothered about that. But actually we should be correlate. The mineral admixtures, it is in the micro level, in the material level, but that is the one of the key factor to achieve your performance objective. Okay, so role of the admixtures, now close 5.2 of the IS456, you can find it. You have the pozzolanas, fly ash, silica, rice earths, and the ground granulated blast. Those are the kind of the mineral admixtures, just to improve that mechanical properties of your concrete. And the mineral admixtures is also known as a supplementary cementitious material, and it added to improve fresh characteristic of the concrete, and to improve the strength and the durability of the concrete, and to decrease the heat of the hydration, and to correct the deficiencies in the packing density, and to decrease the environmental impact of the concrete. So that's the main goal of your supplementary cementitious material. But sometime when we talk about this, we lost the view of the performance objective. I'll correlate it. Don't deviate the route. Okay, just still try to remember it. So these are the those mineral admixtures what I highlighted: fly ash, silica, and the fly ash slags. So this is the around 72% of the fly ash is used in the cement and the building materials in the current scenario. So this, I told you, this just to improve your physical and the mechanical characteristic of the concrete. And next is your chemical admixtures. That is clause 5.5 of the IS 456 you can get. What is the role of the chemical admixtures? What is the relationship between the chemical admixture in our performance-based design? Now, if you look this diagram, what did you observe it? So in the first diagram itself, without any vibrators, person brought the concrete in the pour. It's compacted, self-compacted concrete, you can say. But meantime, this diagram, what I show here, star mark I'm just showing, it's the aesthetic. This is very thin, slender, and a very complicated structural shape. But if you look, it is such a kind of a fantastic finishing. It's really great. But meantime, if you look this kind of a wall, it's a very simple shape. It's rectangular. But can you get any kind of the good strength from this concrete? Finally, we took over a performance-based design. The performance-based design means we should achieve our target strength and life safety, immediate occupancy. All those things we are talking. After doing all those things during the execution in the field, if you put the concrete in such a way that will you get the performance objective? Answer is straightforward, no only, right? At the meantime, why one see when I talk about this entire structural mechanics and this concrete, suddenly a traffic jam photo also is there. You might confuse what's going on here. If you look very carefully in this traffic, you can see one concrete carrying vehicle also here. What is the initial setting time of the concrete? It depends on the temperature. It ranges from 10 minutes to about 30 minutes, depend on the temperature variation. If your traffic is hold for 10 20 minutes, your concrete will be transported around 30 kilometers away. What will do that? The chemical admixture will take a major role. So it can hold your initial setting of the concrete. So the chemical admixture can improve your workability. It can improve your the mechanical characteristics, and so it can delay or it can increase your initial setting time on the concretes. Okay, that's some extra point I'm highlighting here. So this is again a poor construction quality. Because of such issues, you will not get any performance objective during the performance-based design. You might be doing the good design, but practically you will not get any performance goal. So these are the types of the chemical we use: air internal, water reducer, retarder, hydration, and accelerator corrosion inhibitor. So let's have a look at a short video. From here, you'll understand that. Yeah, from here you observe that this is how the chemical admixture and the mineral admixtures took a major role in our construction industry just to achieve the performance objective. Okay, so you need to have a very good workability concrete, having a very good strength, and even if you design it very well for the performance-based design, and if you are not able to pour the concrete properly, everything is waste. So this is the role of the chemical admixtures in the performance-based designs. So usually this topic, most of the books and most of these authors, they are not correlated. So it is very important. You have to be very careful about this. And now, how to deal with the huge earthquake? So here I'll go a little bit fast because this is a repeated portion for yesterday. Since to have the continuity, I mentioned it. So in the huge earthquake, especially for existing structure, you need to increase the damping with the help of the passive energy dissipation device, and allow some kind of inelastic response, what I discussed. Use of rehabilitation and retrofitting utilizing the energy dissipation device. So these are the energy dissipation device. Yesterday I explained friction damper, yielding damper, and the viscous damper, base isolations. So this is a repeated slide. So this is the various of those damper. Just to achieve the performance-based design, you need to introduce such type of device on the structure as a retrofitting scheme. And this is the concentric breast frame. As you know that it has unsymmetrical breast response. And yesterday I did not show you some tests. Let's have a short video. And this testing is, I took this video from my colleague, my friend, Dr. Ashwin Kumar, and he's assistant professor in IIT Roorkee. So from that I borrow this video. So this is the breast testing. You can have a look. Yeah. So these responses are mainly taking a major role in the performance-based goal when you go for any performance-based design for the steel structure. And this is a full setup of the that concentric breast frame testing. So again, this is a BRB. Yesterday I mentioned, and this is a BRB component test, the same diagram, which I borrow from my friend, my colleague, Mr. Dr. Safir from NIT Calicut. And this is a shear yielding device. It has a good strength, energy dissipation capacity, but it has a limited ductility, as I mentioned yesterday. The flexural device, it has a good ductility but low strength and stiffness. So based on that, I developed that device. This also can be used for the retrofitting of your open ground story as well as the non-open ground story structures. And this is the combination of the shear and the flexural components. So now we understand how the performance-based design come off and how to evaluate and how to cross-check a performance objective. Okay, now, as I mentioned in initial upcoming IS 456, what are the things incorporated? And in IS 456 2000, that is dedicated plain and reinforced concrete code of practice. Okay. Meantime, this name is updated to the Unified Concrete Code. Okay, the upcoming IS 456's name is called Unified Concrete Code. And this is applicable for the plain concrete and reinforced concrete. But the upcoming is plain concrete, reinforced concrete, as well as pre-stress and the breeze. This too is the new component added in the upcoming IS 456. And one second. And IS 456, the main goal, it was a limit state of collapse, limit state of serviceability, and the durability. Along with this component in the new IS 456, it considered limit state safety already considered, serviceability already considered, so durability also already considered. Now the new terms are the limit state of the robust, limit state of the integrity. This is the new limit state of the restorability. That's the one I told you. Restorability means in the performance-based design, the minimum repairing cost that is incorporated here. So can you correlate that my explanation there and this one? Nowadays IS 456 also covering some portion of the performance-based design in the upcoming IS 456. So in this restorability, consider about the ductility, environmental adequacy, especially the sustainability point of view, the economy and the aesthetic value. It has considered it. So now the silent features are to get two sets of the design loads, like force and the displacement load has considered, and a 6 limit state has introduced, mandatory for all the buildings, safety, serviceability, and the durability. And the options are the robustness, integrity, and the restorability. And the two approach for the limit state of the safety, strength limits, as well as the strength limits. Okay. So in terms of the force load, this is a dead load, imposed load, wind load, snow load, earthquake pressure, water pressure, blast load, impact load, pre-stressing force, and construction erection load. That's are the force related for load has considered in the upcoming one. And in the displacement load, temperature, sinkage, creep, elastic shortening, foundation settlements, and earthquake ground shaking. This also a displacement load has considered in the upcoming IS 456. Okay, this is my last slides. Thank you to all. And if you have any doubt, and we can have some kind of the short discussion. Madam, the session is hand over to you. Thank you.
Yes, sir. Thank you very much. And in detail, you have very nicely explained the performance-based design. And I think so the participants might be benefited with your lecture. And also you have discussed the some of the features of the upcoming IS 456 code. I request participants to please ask the questions, or you can type in the chat box. There is one question, I think so, that any free software for pushover analysis?
I'm not about the free software, ma'am, actually, but if you go to the CSI software, the SEP 2000 is one of the very basic software for the pushover, and you'll get some trial version, okay, almost 1 month or something. From that, you can do something. And plus, the CSI website, they uploaded many basic instruction videos, like 5 minutes, 10 minutes long. From that also you can learn the pushover analysis. But meantime, if you want to get some kind of data, you can reach to me also, and no issues. But I can't have this line by line, but at least if you have some doubt, you can reach to me also.
What are the criteria for fixing the IO and CI and CP values?
Yeah, immediate occupancy, collapse limit, and the collapse prevention that I mentioned. See, there is no exact answer for that. Please follow the, even IS 1993 don't have the exact value for that. Please use the FEMA 355 or 274, and it mentioned very clearly for the residential building up to 0.5%, 1.5%, 2.2%, like that. But meantime, if you go for the bridge designs, that value will be different. And if you go for the hospital building, that value will be different. Again, if you go for the nuclear power plant construction, that value will be different. So it means there is no any exact value for IOCP and LC for all structure. Each and every building has their own value. So for that, please use ASE 41 or maybe the FEMA 273 or maybe ATC 40. From that, you'll get all these criteria. And if you go to ASE 41, table number 6, okay, table number 6 is the one highlighting all those values.
Yes, sir. Thank you very much. There is one more question: how to perform incremental dynamic analysis?
Yeah. So for the incremental dynamic analysis, see, some people might think that incremental dynamic, you might be using the different ground motion and 40 ground motion, 50 ground motion. It might be no, nothing like that. From a single incremental dynamic analysis can be carried from a single ground motion. For example, if I take the L centro ground motion, and just the normal value, the normal peak acceleration of the L centro might be the 0.36 g, but no need for applying the 0.36 g. You need to scale down. So if you apply exactly 0.36 g, that original ground motion, your structure might be collapsed on the spot in the first step itself. But instead of that, you scale down. Instead of 0.36, you starting from the 0.1 something. That time structure will behave elastic, and then you need to increase 0.1, 0.15, 0.16 like that. You need to do the same ground motion in a different intensity multiple times till the structure collapse. If you recorded all the response and if you plot, you'll get a kind of a half normal distribution. That's how you have to uh, get the structural performance through incremental dynamic analysis. And this is for the one ground motion incremental dynamic. So for a one ground motion, you might be doing 40 times analysis. But similarly, if you use 10 ground motion, 10 into 40, if you 400 times, you need to do the analysis 400 times. So that's how we did the incremental dynamic analysis for the different ground motion.
Yes, sir. There is one more question. Why Indian code has R value for steel as 5 and for concrete is 4.5, whereas in Japan R value is 8.
So actually, if you look to the Japan R value is equal to 8, you have to given a particular value. I'll give it response R value. R means what? R means it's nothing. In my lecture, I mentioned that structural ductility, right? Structural ductility is your R value. It means if your R value is more, means from yield point to the ultimate collapse point, it is more. 8 means more, 5 means reduce. Okay. You know that concrete is a brittle and reinforced concrete structure has a limited uh, deformation. Even in the drift capacity also, I mentioned acceptable is around 2.5%. That's why even for the Indian code, we use the 4 or 4.5. And for the steel structure, again, I mentioned in my slide, acceptable value is from 4 to 10%. 4 to 10%. So we take as a 5. But if you take steel structure also, for the CBF, the concentric brace frame, instead of 5, you can take as a 6. Or for the BRB, instead of 6, you can take 6 or maybe 6.5 or 7. But whatever the R value is equal to 8 for the Japan, they might be mentioning one particular value. Okay, this 8 is for the BRB or might be some other the dissipated devices. But I'm sure that 8 is not for the reinforced concrete.
There is one question. Is your performance-based design can help in reducing the steel reinforcement requirement of the structure?
Yeah. So the performance-based design means it reducing it allowing the nonlinear deformation. Okay. So in elastic analysis or elastic design, of course, you have a very heavy reinforced sections are there. But in case of the performance-based design, we optimize. This is a kind of the optimization approach. We can reduce. We are reducing some kind of your cross section as well as your reinforcement. But reinforcement, you need to look to this one. Balance section under reinforced, that criteria also has to be followed. But it did not mean that always reinforcement will be reduced. But I'm sure that will be the optimized section.
One more question. While defining the plastic hinges in SAP 2000, how much distance we need to take from the end of the column and the beam?
Actually, there is some kind of if you look in the literature, the uncountable times of your this one plastic hinge length calculation formula, you'll get it. Okay, one of the very standard formula is a Perk and a Paule. They developed the plus LP is equal to 0.7 dB. Some formula is developed. People use extensively that one, and then using that formula directly you can calculate the distance away from the foundation or maybe from the beam column joint. Then you can calculate it. Okay. Sometimes if you feel the difficulty to calculate those things, because to calculate that LP value, first of all, you should know the grade of the concrete, you should know the diameter of that reinforcement, and you should know the yield value of the reinforcement. But sometimes if you feel difficulty to calculate, as a thumb rule, we are using a D distance from the interface. D means okay depth of effective depth of that section. That must distance might be 220 or 220 mm or 300 mm. That much distance, as a thumb rule, we can use it. But if you want to use exact value, please use that equation and calculate it.
Any more questions, please? think so. The same thing is that in India, our value for steel is 5, and in Japan for steel it is 8.
Yeah, that's what I said. Steel structure is 8. I'm sorry that I mentioned it. This the 8 was it is not for the reinforced concrete. That is not at all possible. So,
I think so.
any
We
other
are
question?
yes.
I think we are
Yes.
ahead of the 10 minutes ahead of the scheduled time.
No,
12
sir.
is the
No, sir.
ending time.
It is a
Okay.
discussion which is going on. It will be helpful for the participants also.
Yeah.
Yes, we are saying that it is very helpful for us, this lecture.
So if they really want to speak, some of you can be switch on the mic and we can have a discussion. So if you are comfortable,
Please,
that is fine.
yes, if you want to discuss something with sir, you can please discuss with him. Any questions? Especially research scholars who are doing some research work, students.
Anyway, madam, thank you. Thank you for inviting me for this session. And you did great. You organized such a big level of the FDP and many big shots also you brought it. So for me, simply compared to I'm okay, fine, because I'm
No,
just
but
giving some of my.
the lectures you have taken were very nicely. I think so. The way you teach to students in a very
Hmm.
basic manner, it was taught, and I think so. It might be very useful for our participants who are not in the basically in the core structural part, who are in
Hmm.
just civil engineering like environment or geotechnical. They might have also
Okay.
get an idea of these your lectures. Thank you very much, sir. Thank you for sparing your time.
Thank you. Okay. So this is our responsibility.
Thank you, sir.
Okay. Rajesh. Yes.
Yes, thank you, sir. Thank you.
Yeah.
So we will meet for the next session at 12:15 p.m. So please rejoin the session. Thank you very much.
Okay. So then I am leaving the session, madam.
Yes, sir. Yes, sir. Thank you.
Okay. Thank you for your invitation. Chalo. Okay. Bye.